Right, great to see you all here. I mean, Stuart's introduced this EPSRC AkzoNobel Prosperity Partnership, so I don't need to tell you about that bit. Basically, Stuart is the PI. I was the AkzoNobel equivalent, and then Tony Ryan is the other investigator named by the EPSRC on the top thing. I guess this goes with what Stuart just said, that, basically, really thanks to all of you, and, a lot of the glitches are going to be mine. So if there's anything fundamentally wrong, it's probably me. But right, okay. So what are we talking about? AkzoNobel is a large paints and coatings company. You'll hear a bit more about us later on, but I thought it was important just to start, just to say what a coating is. And really, it's so ubiquitous that often we don't think about it. So if we look around the room we're in, and hopefully if anybody's on Zoom, the room you're in there, the surfaces are coated with normal paint, Dulux emulsion, hopefully, giving you a nice white surface in the UK. Your radiator's possibly got a powder coating on it. Your light fittings will have some sort of coating on them. And that's what you actually see. But more importantly here, we're interested in the corrosion, the protection aspect of coatings. Your car's protected by a coating, a paint. Your aeroplane is, your ship is, and so on. So, right, what's inside a paint? Basically, as far as we're concerned, we call paintings coatings quite often, paints coatings quite often. And really a coating has a binder in it. In our case, an organic binder. There are other types of coatings available, ceramic coatings. But what we're interested in is coatings that are based on organic binder. That holds everything together. Typically, you've got some kind of thinner, unless it's a powder paint. And by powder paints here, I mean electrostatically sprayed paints rather than paints that dissolve in water. But you've normally got some sort of thinner that allows you to actually coat the surface. Then you've got a filler, which is providing, in the case of the paints on the walls, here the light scattering and the color, and that's giving you the opacity that you need to actually cover the wall. In the case of our corrosion protection coatings you'll hear about in a while, that's giving often active species that act to stop corrosion once it's started, or block materials traveling through a coating. And then we've got additives that are needed to make the coating work, or are needed on the surface to give you perhaps self-cleaning or something like this. So that's quickly what a coating is. How do they stop corrosion? Once again, fairly critical. Typical corrosion reactions, we've got an iron surface here, and we've got a cathodic and anodic reaction going on. We can stop that in various ways, but there's also the subsequent reaction. Sorry, if you've got chlorine there, you quite often get chlorides formed, and you get a whole load of subsequent reactions, and that's what's the typical sort of rust you're seeing on top of a metal surface. You put a coating on top of it, basically you've taken the iron out of the equation. We're hoping that that coating is going to protect the surface. It's also going to, from the point of view of our active species that are coming out, they're going to absorb onto that surface. Even if you've scribed it as shown there, where you have a scratch, species are going to come out of the coating that are going to stop that metal being available to corrode. Equally, we're hoping that we're going to stop species in being able to travel through the coating and be able to form reactions in this way. And then we've got the sort of passive side. If we can cover the whole lot, then we can create a barrier. Now, it could impede oxygen, it could impede water. In the case of organic coatings, we know that oxygen can travel through them fairly easily, and we know that water can travel through them. So what we're trying to do is we're trying to stop ions, because we need ions to actually complete that corrosion reaction. If ions can't travel, then we may not get corrosive species there in the first place, but we won't be able to complete that electrochemical reaction. So that's how we're trying to stop corrosion. In the case of once you start to look at a coating, then there are a number of rather complicated things happening here. As I've said, we've got the barrier, we've got potential for things like cathodic protection, where we have a material inside the coating that's going to be sacrificially corroding to stop the metal corroding. And then, of course, we've obviously got to get all the normal coating properties right. It's got to actually spread on the surface. It's got to provide scratch resistance. It's no use if the coating cracks. And the toughness of things like this have got to be there as well. So what this project is all about is not necessarily corrosion. It's about how we can understand to formulate coatings better. And taking things from a slightly different point of view, what we actually look at in this, we can start to look at where things are traveling. We can start to look at the desponding we're happening within our coating. We can look at cracks, what's traveling through those cracks. And then we can see how well our inhibitor is actually it's protecting those surfaces. So there are all these particular potential areas that you might want to look at, whether it's corrosion mechanisms that might suggest to us particular ways to protect a particular surface, to far more classic sort of corrosion, for classic coating tests where we're looking at things like adhesion, disbonding. So SusCORD, Sustainable Coatings by Rational Design. It's not that we're irrational now, but we think there's even more rational ways of doing it. And this is what Stuart managed to convince the EPSRC, was that we could have a project with supporting what we'd already been doing, working with the EPSRC and their funding, with equal funding for AkzoNobel. So Sustainable Coatings by Rational Design, we're trying to get these physical chemical properties that determine what the service performance will be. And that's enable us to actually make better coatings in the end and have this digital predictive design that we can then predict how coatings are going to work over time. Within that, we've basically split up into 4 work packages. So each of these sentences basically describes the work package. We're interested in understanding what we can get out of machine learning data, using the data we've got to understand how the coating's working better, and giving us insights into how components in the coating are working that we don't necessarily know from first principles, because a coating is a complicated formulation and there may well be things happening that are not linear single component effects. Can we use machine learning to give us better insight into that? Can we use machine learning to interpret the tests we're doing in a more consistent manner? What we've been trying to do from the start of our work, and I mean, Stuart talked about, the 10 years we've been working with Manchester, but, behind that, there was 40 years that Manchester's been working on corrosion with international paints, with AkzoNobel, with Cortels, with ICI before that. And equally with Sheffield, we've been working on polymers for decades, trying to understand how we can make these coatings better, and other polymer systems as a business been interested in other sides. So this is very much understanding, how we can understand the mechanisms that are actually making our coatings either allow transport or stop transport. The third work package is very much using the high resolution and highly sophisticated equipment that's now available, that wasn't available in the past, to look at what are often very complex systems to start with. So can we look at a fully formulated coating that works very well? Can we make it fail and understand what's caused that failure? And that then gives us new insights for other ways to tackle this system. And the final one is nowadays modeling is very capable, and trying to use modeling to take the information we've gained from the other work packages and take models from the ground up to give us insights into how the systems are actually working. You'll hear about that, all those 4 work packages later on. The team, you've basically seen Stuart. Tony has stood up earlier on, so you've seen Tony. We have the 4 work packages, and led by Douglas, Richard, Giron, and Flor. And then we have a series of other academics involved and postdocs. So those are the 4 work packages. Just, these are not happening in isolation. I mean, I've sort of touched on this, but the mechanisms that if we find things that work, if we find things from the sophisticated analysis, can we then understand what the polymer effects are happening that are causing those mechanisms to occur? So there's obviously interactions between those. And in all cases, we've got more data and more understanding, or more data and more information that can go into our predictive design and testing. So the thing is all together, what we've got is basically our current knowledge is where we're starting from. At the end, we're hoping SusCORD is going to deliver this toolkit for rational design of coatings that will have been through all these interactions in here. I just thought it was worth quickly just touching on the methodology we sort of developed over the last 10 years. We've as a company, and is in order to actually get our money into it, we need to see what application it's going to impact on, how it's going to actually affect the business. And I think, as Richard said yesterday, having a real challenge actually helps to focus the scientific questions you're asking. So normally we're taking a specific coating and using that to start with, but then we're quite cruel. If it's not of interest to us, but on the other hand, if it's equally not as interesting in terms of the science can be done with it. So if I ask somebody to look at something that's impossible to look at, with the equipment available now is not very constructive, however valuable it might be to us. So we try to make systems that are both commercially valuable and that's scientific, and it's finding that sweet spot that's been productive, but is often quite a lot of work. We hope to get some general phenomenology out. We then quite often think about simplifying things. So once we've shown that it works, can we really prove that by actually tweaking the parameters that seem to be important? We then would look at how can we model that, because once again, if you can produce a model, so this is now a computational or a data model that reproduces the facts, we've got more confidence that the hypothesis we've made, the mechanism is correct. And then typically we'll be reevaluating. So that's when it comes back into, AkzoNobel, we try and use these ideas to make better coatings. And the final test is that coating better? And bear in mind, we were going for one application. Then at the end, having found it works for this one application, can we generalize that? Have we learned a new rule? So that was really where I wanted to end. And as Stuart says, I'll be leaving. So Claudio De Lulo will be taking over my role from AkzoNobel, and you'll hear from Claudio a bit later on.